This is joint work with Havard Bjerkevik, who is a postdoc at TU Graz. He recently graduated from NTNU, and Havard has been doing some great work in TDA, especially on the theoretical aspects of multi-parameter persistence. And in addition to collaborating with me on this project, Havard has also collaborated with me on these slides. He shared with me some early, or rather, an earlier version of this talk that he gave, and that was a starting point for preparing this talk. So I want to acknowledge his contribution to the slides as well as the work. Anyway, we're going to be talking today about LP distances on multi-parameter persistence modules, and I'd like to start from the very beginning, in a sense, and just talk about what TDA is. So to me, TDA is the following. I start with a data set, and from this data set, I construct a diagram of topological spaces, call it F, say, and I build F in such a way that the topological structure of F captures some information about my data that I care about, usually some kind of geometric information. And then I analyze F using usually well-known tools from topology and abstract algebra, for example, homology with field coefficients or the connected components functor. Now, the best known case of this, I think, is persistent homology. This is the case where F is what we call a filtration. Filtration is just this linear shaped diagram of topological spaces that looks like this. And in persistent homology, after obtaining this guy, we usually apply homology with field coefficients to each space and each inclusion map in the filtration. And so to share with you the familiar illustration of this pipeline, we start with, say, a point cloud. Here, the point cloud lives in R2. And given that point cloud, we can associate to it, say, the Vietoris-Rips filtration or the check filtration. And then applying homology gives us this linear shaped diagram of vector spaces like this. And we have a structure theorem for these diagrams that tells us that the isomorphism type is completely described by a persistence diagram, this collection of intervals, rather this collection of points in R2, which you can also think of as a collection of intervals in R. Multi-parameter persistent homology is the case where F is what we call a multi-parameter filtration. For example, this grid-shaped diagram of vector space, of topological spaces over here. You guys can see my mouse move, can't you? Okay. Yep. And so just as in the case of ordinary persistent homology, we can apply homology with field coefficients and get a diagram of vector spaces of the same shape. And these multi-parameter filtrations are arising quite naturally in a lot of places. And so I think they're very interesting in TDA. One of the main motivations to consider them is in the study of data with outliers, or data with variations in its density from region to region. And if time permits, we'll talk a little bit more about this later on in the talk. Also, and the idea there is that trying to handle density as well as scale is going to give you a second persistence parameter. This also arises when we're looking at data with a real valued function. For example, if your points are atom centers in a protein, you might consider a real valued function of partial charge, or you might consider your real valued function to be a time function when you're looking at time varying data. So there are a lot of places that where these things are coming up. And it turns out, though, that we don't have a good notion of a barcode for multi-parameter persistent homology. And that makes it not straightforward and sort of interesting and challenging to actually carry out the program of topological data analysis in this setting. One of my main research goals is and has been for some time to make multi-parameter persistent homology practical. And there's been very good recent progress on this, especially on the computational end, but applications are very much still in their infancy. There aren't a lot of convincing stories yet about applications of multi-parameter persistent homology. I think a lot of that is because real essential computational progress has been so recent, and it is still very much in progress, I think. So things look different now in the computational landscape than they did 2 years ago in qualitative ways, I think. And I think so some doors have only recently opened in these directions, and I think that people who care about these things the most haven't necessarily taken the time to walk through those doors in the right way. So I think the prospects for real practical progress are very good, and I'd be happy to talk with any of you about that at some point. But this talk is mostly a theoretical talk, but I'm going to speak to some questions that I think I'm going to speak to some practical issues, and I hope that this work is going to be able to contribute something on the practical end. Okay, so before going forward, I want to clarify precisely what I mean by a multiparameter filtration and a multiparameter persistence module, because I'm going to use a couple of different definitions throughout this talk, and I want you to understand what I'm doing there. So I'm going to let P be a product of n totally ordered sets, where I take the usual partial order. So A is less than or equal to B in P if and only if the ith coordinate of A is less than or equal to the ith coordinate of B for all I from 1 to n. And then I'm going to define a d-parameter filtration to just be a diagram of topological spaces indexed by P, in other words, a functor. And I usually require that functor to satisfy some kind of containment property, although for what we're doing today, I don't think that's too important. And then similarly, a d-parameter persistence module is a functor from P to the category of K vector spaces for some field K. And the case that I've illustrated in these slides so far is a case where P is the product of the natural numbers with itself. And in this case, the persistence module is this nice grid-shaped commutative diagram here. We're also interested in the case where P is equal to R2, or Rn, and you should think of that as being very much like this case, except you have a vector space attached to every point in the plane. So there are too many arrows and you can't draw a nice picture like this. Now, this is a talk about metrics, and metrics on multi-parameter persistence modules are really important both in theory and in practice of TDA. And on the mathematical side, I would say that somehow what really gives the mathematics of TDA its unique identity is the emphasis on metrics. Like, we typically care more about whether two objects are close in some metric than when, as opposed to whether they're isomorphic on the nose. Because in TDA, our objects are only barely isomorphic on the nose. And we're always working in these kinds of noisy settings. And so concretely, metrics in TDA are used for stability and inference results. So they're very important in formulating the theory. And they're used to provide approximation guarantees for computational methods, for example, in the work of Don Sheehy on sparse-width filtrations. And they get used quite a bit in practical computations. Like, a lot of the applications to real data you see are using a computation of a distance somewhere in their pipeline. And so we want to ask here, what metrics should we use in multi-parameter persistence? This is a question that people have been asking for quite a while. I've been asking that question in different ways for several years, but I still think that there's some interesting things to say about this question. And to try to tackle this question, we're going to start with what I think is the most important metric in the one parameter setting, the bottleneck distance. The bottleneck distance is a distance on barcodes, but every persistence module has a barcode. So we can think of it as a distance on persistence modules. And as we'll see in a moment, this is defined in terms of an L-infinity norm. And one of the reasons that we care a lot about the bottleneck distance is because the bottleneck distance satisfies a nice stability theorem. And this is the theorem. This comes in various versions and in different levels of generality. But I'm going to state a version for functions. And this essentially was the original stability theorem for persistent homology. It says that for any topological space and functions f and g on X, the sup norm distance between f and g is greater than or equal to the bottleneck distance between the persistent homology modules of the sublevel filtrations of f and g. Sublevel filtration is defined like this. It's an R-index filtration whose value at parameter a consists of just the subset of X where the function value is less than or equal to a. And as I think many of you probably know already, this theorem has some very nice consequences in terms of point cloud data. For example, via the nerve theorem, you get a stability theorem for check complexes with respect to the Hausdorff distance. And with a tiny bit more work, you can get a RIP stability theorem with respect to the Gromov-Hausdorff distance. This is really a key result, and it's had a big influence in a lot of applications. Okay, so now let's talk about generalizations of the bottleneck distance. So as I see it, there are two major directions of generalization of the bottleneck distance in the literature, both of which are quite well known by this point. First, you can generalize the bottleneck distance to an LP version that is called the Wasserstein distance. I'm going to denote it like this. And this is, because I want to use this notation, well, this was the reason that I chose this notation for the bottleneck distance. We'll see that the bottleneck distance is like the p equals infinity case of this Wasserstein distance. And in a different direction, the bottleneck distance generalizes to multiparameter persistence modules, and in fact does so in a couple of ways. The two most, at least a couple of ways, but the two most prominent ways, and the ones that I'm going to discuss here, are it generalizes to what's known as the interleaving distance and to the matching distance. We'll denote by di and dm respectively. And so I've organized this information about generalization into a little table here. Right, so as we move to the right in this table, we generalize from the bottleneck distance to the p-Wasserstein distance. And as we move down in this table, we generalize from the bottleneck distance to these two different distances on multi-parameter persistence modules. And so you notice that something is missing over here. And our goal here is to fill in this box, and to do so in a way that is principled and extend some of the nice theory that we have in these other cases. And so one important thing to say for this talk is that for each of the generalizations here, like this box here and this one, there's a stability result that looks a lot like this function stability result that I showed you on the previous slide. And so one of the things that we're going to do when we give our generalization is try to also give a stability result in a similar spirit. Now, so what I want to do next is define these distances here and explain to you why we might care about them a little bit. Okay. So I'm going to start with the p-Wasserstein distance. We're going to start with this box first. And so the first thing to say is that actually there are a few different variants of the p-Wasserstein distance on barcodes floating around in the literature. The one that I'm going to talk about is, I believe, due to Robinson and Turner. In fact, Kate Turner gave an online talk in the Applied Topology Research Network last year, explaining all the different ways that this was a nice choice of a definition for the p-Wasserstein distance. I believe this definition first appeared early on in the TDA literature in the p=1 case in work of Collins and company coming out of Stanford. And you're right. Okay, so here's how we define this. First, let me talk about matchings, because we need to talk about matchings to define this Wasserstein distance. Suppose I'm given persistence diagrams B and C. So think of B as, say, the orange and C as the blue. Then a matching between B and C is just a bijection between subsets of C. So we can illustrate this like so. So in this bijection, all the blue points are matched, and then there's just one red point left unmatched. Or I don't know if you want to call that red. It's somewhere between red and orange. But anyway, so to define this, this p-Wasserstein distance, we're going to associate to each matching some kind of cost function. And this is this big expression that, I didn't highlight that very well. This big expression over here. And then I'm going to take the minimum of this expression over all matchings. And what is this? Let's just talk through it because it's important. So for each matched pair of points in this matching between barcodes, I'm going to take the p-norm of the difference between this matched point. So this is a p-norm in the plane. And I'm going to raise that to the p-power and take the sum of these for all such matched pairs. And then what am I going to do with the unmatched points? Well, I'm going to pretend that they're matched. Right? For example, for this point, I'm going to think of him as matched to his closest point on the diagonal, and then do the same thing. Right? Take the difference between the matched points, take the p-norm, raise to the p-th power, sum up, and then finally, I take the p-th norm of everything, sorry, the p-th root of everything, and that is my cost function. Give me 1 second. You guys ever have this problem in Zoom where the pictures of people's faces kind of get on top of what you're trying to do? Yeah, I think I solved the problem. Okay, so that is the definition of the p-Wasserstein distance, and that is a way of saying this that maybe is slick relative to the alternatives, but not so transparent. So just to make this seem a little bit less funny, let me give a different interpretation. What's really going on here is that for all the matched pairs, I want to treat the x coordinates and the y coordinates of the differences separately. Stick those all into a big vector, and then take the p-th norm of that. That's really what I'm doing here. That's really what's hiding behind these appearance of all these different p's. This is a p-norm of some vector derived from the matching. All right. So why would we want to work with this Wasserstein distance on barcodes when we already have this lovely bottleneck distance? Well, the bottleneck distance has some defects that may not be so nice in application. So first, it depends only on the largest distance between matched points. So if you have persistence diagrams that look like this, where everything is tightly matched, except this point, we have this like stray guy that doesn't get matched, well, the bottleneck distance is going to depend only on the magnitude of this unmatched guy, its distance from the diagonal. All right, so this is like a lack of robustness for the bottleneck distance that you might not want when you're working in applications. Like it might be that this kind of signal is not what you care about. Also, the bottleneck distance is insensitive to the number of smaller unmatched features, right? Like it just cares really about the unmatched feature furthest away from the diagonal. And these are often undesirable features, as I understand it. And as a result, you see a lot of practical applications that are using the p-Wasserstein distance, usually for p equals 1 or 2, in place of the bottleneck distance. And yeah, there's a host of papers. I think we have 8 references in our paper to papers that are using this, and I'm sure there are many more that we haven't found. But another reason to use or to take seriously this p-Wasserstein distance is one that was explained recently. There's this cellular stability result for these p-Wasserstein distances that appears in a paper of Scraba and Turner from last year. And I think this is a really nice result. It's very natural, and I expect that it's going to be very useful in TDA. It's somehow so nice, and the statement is so simple that it's surprising that it wasn't discovered before, because people have been doing this kind of stability stuff for, I guess, maybe at least 17 years. But what the statement says is, for any finite CW complexes X and monotone functions from the set of cells of X to the real numbers, the p norm of the p, let's say the p distance between f and g is, well, I guess a better way to say it is the p norm of the difference between f and g is greater than or equal to the p-Wasserstein distance of the barcodes of the sublevel filtrations of f and g. Now the sublevel filtrations are understood to be taken cellularly, right? And what monotone means here, this is just a natural requirement on the functions that ensure that the sublevel filtrations are indeed CW filtration. So like you don't want a cell to appear before the cells that it attaches to, and this condition ensures that. Okay, so yeah, so this is a theorem that looks a lot like the ordinary stability result, but it's for CW complexes, and it is given in terms of p everything instead of infinity everything. And in this paper, the authors talk about a lot of applications. I guess there's 4 main classes of applications. And to illustrate how natural this is, I just want to talk briefly about an application that they have to grayscale images, which is very simple. So imagine you have an image like this. Well, people often do sublevel filtrations on the pixel intensities of a grayscale image and use that as an invariant in machine learning or some kind of data analysis. And what the earlier stability result says, well, let me put it this way. Like, suppose that you take 1 pixel. I've got these white pixels here, and just suppose you take that 1 pixel and you change that from white to black. That's a very small change in this image somehow. It's a small change in the data, but it somehow creates a maximal change in the L infinity distance between the 2 functions. And so the stability theorem only says, the classical stability theorem only says something very weak about this, but relatively speaking, the L1 norm is going to see, the L1 norm on the functions is going to see that only 1 pixel has changed and see that in a relative sense as a small change. And so you get this stronger stability result in this case. And I think it's almost, as far as I know, we didn't understand this kind of thing before this work, and it's like almost funny that we didn't, but now we do. And I also want to mention that, this is not the first Wasserstein type stability result for functions in the literature. There's an earlier one that is due to Cohensteiner and company. It concerns Lipschitz functions. It has a bit of a different flavor, like infinity here appears over here where I'm highlighting instead of p, and there's an exponent up here. And in my view, this result is to my understanding, seems a bit more natural. But this other one has also been really influential on people, and as you can see, came out quite a bit earlier. So, okay, so that's stability, and hopefully I've made the case that these things are interesting in practice. Now let's talk about the multiparameter setting, or other direction of generalization. So I said we have 2 distances that we want to define, and I'm going to start with, what am I going to start with? I think I'm going to start with the interleaving distance. Yes. So I'll go through this quickly because I assume most of you have seen it, but interleavings are what are used to define the interleaving distance, and they're easy to draw for persistence modules indexed by the natural number. So a 0 interleaving looks like this. It's the data of a pair of inverse isomorphisms between 2 modules. 1 interleaving looks like this. It's this crisscrossing diagram of vector spaces extending the modules, where when you cross over, you go to the right once in either direction. 2 interleaving is the same, except when you cross over, you go to the right twice. Neat. Those are interleavings. Now, if we want to generalize this, it's hard to draw the whole picture at once because there are too many arrows like before, but you can define this in the same way for n-parameter persistence modules. And in this case, for delta greater than 0, or it should have said greater than or equal to 0. In fact, a delta interleaving between n-parameter persistence modules is just a linear map with domain one of these vector spaces in either module for every vector space. And these maps sort of map to the same index, but with a shift, right? So if you're at vector space MA in M, then when you map to what I call A plus delta arrow here, where delta arrow just is the vector in Rn, each of whose coordinates are delta. So we shift forward uniformly in every coordinate direction. And that's how we define interleavings. And then, but we require that for this collection of maps to be an interleaving, everything in sight has to commute. Okay, so you have all the kind of compatibility conditions you want. And really, these assemble into a pair of natural transformations, but I thought it's notationally easier to just represent it this way. Fine. So then the interleaving distance between modules M and N is just the infimum over all delta, such that there exists a delta interleaving between M and N. And that's the distance. It has nice properties. It's an extended pseudometric. It descends to a proper metric on isomorphism classes of finitely presented multiparameter persistence modules. So it's this well-behaved thing. And in one of the key theorems about the interleaving distance concerns what happens in one parameter. This theorem says that on one parameter persistence modules, the bottleneck distance is equal to the interleaving distance. And this is nice because the interleaving distance is way more general, but it tells us that in the familiar case, it reduces to this very well-known thing. So this theorem also is called the algebraic stability theorem. And yeah, it's used a lot in TDA. So now, and I should mention also that this theorem, in fact, is a generalization of the functional stability theorem that we looked at, the first stability theorem that we saw. Okay, so it's an algebraic generalization, essentially. Now, it turns out that there also is a notion of functional stability for the interleaving distance for multiparameter persistence modules concerning some kind of generalization of the sublevel filtrations that we saw already. And so this is a result from my thesis work, and it says, for any space X and functions from X to Rn, the interleaving distance between the sublevel filtrations of, or rather between the persistent homology modules of the sublevel filtrations of F and G is bounded above by some kind of sup norm-like distance, right? So the way that we're defining this distance on the functions is we just take the sup norm on each of the components and then take the supremum over all component functions. This is a natural way to extend a sup norm to Rn valued functions. And here the sublevel filtration is, the definition looks pretty much like the one that we had before in the one parameter case, except now we're looking at these sublevels in the Rn setting. So this is understood to be the partial order on Rn. So that's part one. Actually, this whole result is a triviality. It took a long time to articulate here in this presentation, but it doesn't really take much longer than that to prove. There's not a lot to it. What is less trivial is that it turns out that at least when the underlying field over which we're doing, over which we're defining our persistence modules is prime, any distance d with the same stability property as shown here is a lower bound for the interleaving distance. So this is a characterization of the interleaving distance in terms of sublevel filtrations. It's stable with respect to them, and it's the largest stable one. And this is, in my mind, this provides some justification for considering the interleaving distance as opposed to any number of other alternatives that you might consider. So let's talk about computation for a second. Turns out that computing the interleaving distance on two parameter persistence modules is NP hard. This is a nice result of Havard and also of Magnus Bottleneck and Michael Kerber from a couple of years ago. And so we would really like to be able to do computations with the interleaving distance, but as far as we know, that's going to be hard, at least for big modules. This is what's expected based on that result. So that motivates us to consider some kind of more computational surrogate for the interleaving distance. And the one that has emerged as the favorite in the last few years is what's called the matching distance. It actually was defined before the interleaving distance. The paper was published in 2013, but I don't remember when the work was done, maybe 2010. And so the matching distance is defined like this. It's sort of nice and simple, but it's easiest to define when we work with R2 index modules. So we're going to consider lines of positive finite slope through the plane. Right? I'm just going to define this for the R2 case, even though the definition is more general. It's easy to define here. And I'm going to look at some line, restrict my modules to this line. Now I get one parameter persistence modules, and I can take the bottleneck distance between those modules, right? These one parameter guys have barcodes, and so there's no problem there. And I take a weighted version of this bottleneck distance, but if you parameterize your line L the right way, you can hide that weight in the parameterization. And then I take the supremum of this quantity, this bottleneck distance, over all such lines, and that's my matching distance. That's it. And so it's this nice way of extending the bottleneck distance to multi-parameters without a lot of pain. And it turns out that this matching distance is a lower bound for the interleaving distance. It was already implicit in this work that introduced this, but Landy proved this explicitly. It's an easy application of algebraic stability. And so what's nice is that this is computable. And in fact, Andrea Cherry and his co-authors developed a quad tree-based algorithm for computing these matching distances on 2-parameter persistence modules back in 2011. And recently this was revisited by Michael Kerber and Arnar Nigmatov. They sort of use the same high-level idea, but they do things in a way that is a bit more efficient and maybe a bit more transparent. And they show that, again, just in the 2-parameter case, you can approximate these distances. And Arnar has a nice code called Hera for computing Wasserstein and bottleneck distances. And in his code, he also can handle these matching distances now, which is great. Also, you can compute these for bipersistence modules exactly in polynomial time, although the state of the art isn't that practical yet. I think you can do better than the state of the art. And we don't have results for the n-parameter case, but I think among specialists, these results are thought to be likely to extend if somebody's willing to be brave enough to work it out. And there have been some applications of this matching distance. Here are a few, but not a ton yet. But I think the door is open for applications because of some of these nice developments on the software end. So hopefully we'll see more. But now with this background out of the way, let's talk about motivation for LP distances on multi-parameter persistence modules. And so this project started with some pretty concrete practical motivation, which is, although I think the prospects for using the matching distance more in applications are good, the fact is that the matching distance inherits some of the undesirable properties of the bottleneck distance that we talked about, right? This lack of robustness and this lack of sensitivity to small features. And so the hypothesis that got this work underway is that an LP extension of the matching distance ought to perform better in applications. Maybe not all applications, but many. This is sort of what I expect to be true, although we've not verified this yet. So that's the main practical motivation. We also have some theoretical motivation. I'm just going to talk about it quickly because there's so many different definitions floating around here. Maybe we'll talk more about it at the end of this time. But so there's a 2-parameter filtration that interests me a lot called the multicover filtration, multicover bifiltration. It's like a density sensitive bifiltration. It turns out to have a nice stability property with respect to outliers, which is formulated with respect to the interleaving distance and what's called the Prokhorov distance. This is like a close analog of, say, like stability of offset filtrations for ordinary persistent homology, but it's density sensitive. This is a recent result by Andrew Bloomberg and myself. And you can actually compute this guy. Again, I might talk more about this later. You can compute it at least in smallish examples, like 200 points in R2, you can handle, for example, and that's thanks in work to several people. But so you have this good stability, but if you do some computations, you quickly start to see that adding just a few outliers leads to a lot of non-persistent features entering into the homology modules. So you have the stability, but still a lot of stuff is appearing quickly. And so it's natural to ask, well, so the interleaving distance systematically ignores the small scale stuff. But I want to ask, can we use an LP extension of the interleaving distance to enrich our stability theory in a way that can kind of quantify some of these phenomena? So this is a theoretical motivation. Okay, so this was a really long treatment of background. So let's hurry along and get to our distances finally. Our distances, there's going to be two of them, just like there's a matching distance and an interleaving distance. We're going to call them the presentation distance, denote it like this with a P up front because it's supposed to be like the interleaving distance. And then the P matching distance. And hey, look, there's a typo in the slides. That's supposed to say DMP, not DIP. Or we're also calling it the Wasserstein matching distance. Before I define them for you, I would be remiss not to talk about some related work in this direction. There has been considerable related work which has inspired us and I think given us the context that we needed to do this work. So I'm going to just talk about it quickly in the interest of time. So first of all, Bottleneck, Scott, and Stanley, they're the first people to try to generalize the Wasserstein distance to multi-parameter persistence modules. And in fact, they succeeded. They didn't just try, they did it. And they go further and generalize to diagrams of vector spaces indexed by arbitrary small categories, I think. And this is interesting work, which I recommend for you to check out, but it's got some key differences to our work. It doesn't generalize either the interleaving distance or the matching distance. And in various ways, it's qualitatively different than our distances. And I think just in the interest of time, that's all I'll say about this. So this, if you're interested in the work that I'm talking about today, it's also worth checking out this work and seeing how they're the same and different. But okay, Skraba and Turner in the same work that I talked about, there's like a second half of their paper that's more algebraic in spirit. And they explore extending this Wasserstein distance in various ways. And the way that they explore this is they give a characterization of the Wasserstein distance on barcodes that involves some algebra, and then they set up a axiomatic framework to say, like, what would you need to extend this version of the Wasserstein distance in a way that gives you the triangle inequality? And their approach to extension requires you to make a choice about a choice of what they call a p-norm on the modules. And so they're seeing like when the p-norm will give you a triangle inequality. But at least for multi-parameter persistence modules, they don't actually make a proposal of what p-norm to use. So there's no multi-parameter extension given, but still it's an interesting set of ideas that's related to what we do here. And actually it's got relation to this work of Bottleneck at all. Like the approaches are somehow similar in the p=1 case, and then more different for other p. And then finally, one thing somebody can do here is you can map the persistence modules into a linear space where you have a p-norm and then use that p-norm to define distances. Like there's a lot of this kind of featurization being done in TDA literature, and there are a few works considering this type of thing in the from like an LP standpoint as well for multi-parameter persistence modules. So this this maybe is an alternative approach to this p Wasserstein distance that we're about to introduce with some kind of different properties. But I think in applications, it would be really nice to compare some or all of these to what we plan to do. Fine. Now we come to the definitions here. So I'm going to define the matching distance first, because defining this is the p matching distance, because it's really easy. Here's the definition of the matching distance from before. And to define the p matching distance, all I'm going to do is replace the bottleneck distance in this definition with the p-Wasserstein distance. That's really simple. That's all we do. I could have told you about this, I guess, 10 or 20 minutes ago. And maybe it seems like just the obvious thing to do. In retrospect, we claim that it is indeed a good thing to do. But I think for a long time, before we really did this work, it wasn't obvious to me whether when you're working in this p-Wasserstein setting, that you really want to be looking at a supremum over here. And we claim that you have good justification for doing that. And that justification will involve in part our p-presentation distance, which I'm now going to define. And so the natural domain of definition for this is for finitely presented Rn indexed modules for any n, but to simplify things, and so I can draw pictures, I'm going to consider the n2 indexed case. Right, this allows me to draw diagrams of spaces in a nice way. First, we need maps between persistence modules. We just define a morphism of persistence modules to be a natural transformation. So concretely, if you have a diagram like the white one and a diagram like the blue one, the natural transformation is the data of all these pink arrows mapping from white to blue at each index and making everything commute. This gives the persistence modules the structure of an abelian category. You have direct sums, you have co-kernels, you have other nice things. I think that's all I need for the moment. And to define the presentation distance, I need to define presentations, which means I need to define free modules. So first, let me call a quadrant persistence module one that looks like this. So there's some minimal index with a copy of the field K. Outside of that index are zeros everywhere. Above that index are other copies of the field K connected by identity maps. It's some kind of like indicator module for the quadrant whose lower left corner is here. And then a free module is just going to be one isomorphic to a direct sum of these modules. So I've drawn one here where the lower, you have two summands and their lower left corners are here and here. You can think of this schematically in terms of these two quadrants. Good. And now, there's a nice notion of basis of free modules in this setting, which we'll need. Briefly, so a basis is a minimal generating set, essentially, for these modules. And what is a generating set? Well, we'll say that a set of vectors in the module, meaning vectors living at any of these indices, generates the module if any vector in any one of these vector spaces, say this one over here, is a linear combination of shifts of the elements in my set. So I might have some elements of my generating set live over here, or over here, or over here. And if I can shift them all forward into this vector space where the vector that I care about lives, and then express this vector as a linear combination of those shifted guys, that's what I want. And if I can do this for every vector, that's then I say that this set of vectors generates. Again, because that was a mouthful, I'll say again that a basis for the free module is a minimal generating set. And this is just, if you speak algebra, this is essentially the natural and obvious thing. So then a presentation of a bi-persistence module is a morphism of free modules, say F, and with the property that the co-kernel of this morphism is isomorphic to M. Okay. Again, this is what it means for F to be a presentation of M. That's simple enough, but for what we do here, we're going to think of like we want to think of presentations with respect to bases. We want to think of them in more concrete terms. So suppose that I'm given finite ordered bases for F and G, the domain and the codomain here, call them B and C. Then it turns out, using ideas that are essentially that are really similar to ones from ordinary linear algebra, we can represent F with respect to these bases as a matrix with field coefficients. And I'll skip the details of how you get this matrix, but again, it's kind of like how you do it in ordinary linear algebra. And because we're in this graded persistence setting, we're gonna have a little more data attached to our matrices. We're gonna associate to each row and each column a label. And because I said we're working with N2 index persistence modules, the label will live in N2. If we were working with Rn index persistence modules, the label would live in Rn. And these labels are obtained as follows. The column labels are just going to be the grades of the elements of the basis B, and the row labels are going to be the grades of the elements of the basis C, right? These bases for F and G. Okay, so you're essentially remembering where the basis elements of these modules live. And with this matrix representation, you actually end up encoding the morphism up to natural isomorphism, and therefore you end up encoding its co-kernel. So this matrix version of the presentation captures M up to isomorphism, and that's nice. Okay, now we know what presentations are, and let me explain how we use them to define an LP type distance on modules. So first, I'm going to define some kind of LP type distance between two presentations. I'm going to let P and Q be presentations with the same underlying matrix. So the matrix is the same, but the labels can be different. Let me write the labels of P as V1 through Vm, labels of Q as W1 through Wm. And here's what I'm going to do to define this distance. Essentially, I'm going to take, so you have this vector of points in Rm, and I'm going to put everything into a single big vector where the coordinates are in R. Okay, so if this has length M and I'm working with Rn index modules, then I'm going to stick all these coordinates of the labels into one vector in Rmn. Do the same for this. And then I just take the P norm of those big vectors. This is just another way to write that down here. So right, just stick everything into vectors, take the P norm, and then to get some kind of distance between my modules, I take the infimum over all presentations. So I'm going to take get a distance between modules M and N, take the infimum over all presentations for M and N with the same underlying matrix, possibly different labels, but same underlying matrix, and then take this distance between those presentations. And that is some kind of not crazy looking distance between modules. But it turns out not to satisfy the triangle inequality. And so what we do is we do the obvious hack to this distance to make it satisfy the triangle inequality. Like we consider the metric generated by this distance that doesn't satisfy the triangle inequality. So essentially the distance between M and N is going to be obtained by considering all finite sequences of modules that start at M and end at N. And then you take this distance here, this hat distance between consecutive pairs in this sequence, sum them all up. Right? This is just like a generic trick for converting a distance that doesn't satisfy the triangle inequality to the triangle inequality, to one that does satisfy the triangle inequality. Okay, that's our distance. So we dealt with this triangle inequality issue in a pretty naive, simple way, but we think this is a good way to do things. And so here is our first main theorem, which it's got 4 parts, and essentially it says that these distances indeed generalize the ones we've seen, and they also extend Landy's inequality relating the matching distance and the interleaving distance. So first, part 1 says that in the p equals infinity case, our presentation distance is equal to the interleaving distance. Actually, this result isn't new. It was proven in more generality in my thesis work. And so already, like all of this story appears in the p equals infinity case without, except for taking the extended metric generated by the distance. That appears in this earlier work. There's kind of inspiration for this stuff, but this paper that we're going to be finishing gives a new, more conceptual proof of this that I prefer. Okay, the matching distance, the p matching distance in the infinity case is equal to the ordinary matching distance. That's true by definition. Then all these distances are equal in the one parameter case. They're equal to the p-Wasserstein distance. That's what you want. This first inequality, that this presentation distance is equal to the Wasserstein distance, is not exactly trivial. This is a generalization of the isometry theorem that we saw before to p-index persistence modules. And in fact, it has a new proof. I mean, the proof is closely related to other proofs, but I think it's okay to call it a novel proof that I think is nice. But it uses an interpolation argument that's similar to what Scraba and Turner use in their cellular stability proof. So at least there's this relation. And then 4 says that this distance, the p matching distance, is a lower bound for the p interleaving distance. And this is also not trivial. It's not especially hard to prove, but in any case, it's true. And so that tells us that we can fill in this grid over here, just like so, and we can even put an inequality over there. So we've done our business of generalization now. And so what else to say? We're getting towards the end of the talk, but there are still a couple of major things to say. It shouldn't take too long to say. Right, so first, you can actually approximately compute this matching distance. I mentioned this algorithm of this p matching distance, ours. You mentioned this quad tree-based algorithm of Kerber and Nigmatov. Well, it extends really painlessly to be able to compute this p matching distance on bi-persistence modules. And there's like a nice bound that is a variant of one in their paper. It's proven in a very similar way. They use algebraic stability to prove their bound. We use our kind of LP generalization of algebraic stability. And I won't say anything more about the details. We conjecture that this is exactly computable in polynomial time. On the other hand, we conjecture that computing this presentation distance on 2-parameter persistence modules is NP hard. That would generalize Hilbert's result. And we haven't worked on these kinds of things, at least I haven't. But these are just the kinds of things you expect to be true if you have been in this world. Okay, and so now here is the last major result of this paper that I say is going to come out this month. It's the stability result that I promised you, and it actually has a universality part to it as well, and it concerns just 1-parameter and 2-parameter persistence modules. And so inspired by Scraba and Turner, we work in the cellular setting. So let X be a finite CW complex. And first, I need some kind of notion of a P norm of a function from the set of cells to this to Rn. And this is essentially the kind of thing that we saw before. Like we take the values of this function on all cells. Like for each cell you have, oops, what happened there? We're mapping into Rn. So for each cell you have n values, you stick them all into a big vector, you take the P norm of that, and that's the P norm of this function. And then the result says that if you have any functions from the set of cells of X into Rn, and they're monotone in the same way that we saw before, so you have a well-defined sublevel filtration, then the P norm of the difference between these functions is an upper bound for our P presentation distance between the homology modules of the sublevel filtrations of these functions. So this is a result that's very similar to what Scribe and Turner did, except it lives in the n parameter, sorry, in the 2 parameter setting as well as the 1 parameter setting. And so is it an extension of their result as I've written it? No, not exactly, because their result actually considered homology in all dimensions at once, and ours is just considering it in a single homology dimension at a time. And in fact, for n equals 2, this turns out to be false as written if you consider all homology dimensions at once. But if you put a 2 over here, then it'll still be true. Okay, that's part 1. And then part 2, this is nice, I think. This actually is the largest, this p presentation distance is the largest distance satisfying this. This is the universal distance with the same stability property. So this is some, I think, very reasonable sense in which this is a distance that is reasonable to choose for your LP extension of the interleaving distance. Now, this result also looks like the stability theorem we saw for multiparameter persistence, and however, whereas part 1 is easy in that setting and part 2 is not so easy in that setting, the opposite is true here. Like, this result turns out to not be trivial at all. There's some delicate parts to it, and it's kind of the most intricate math of the whole story. Whereas this ends up being like just an easy lifting argument. So, all right, that's the story now. I think I'm out of time. I've pretty much used up the whole hour, so I won't outline the proof of stability. And I won't tell you in any more detail about this story concerning the multicover by filtration. Maybe some other time. So we're going to write a follow-up paper that concerns applications to the multicover by filtration, and I'd love to tell you about it more some other day. But I'm going to stop here and leave you on this slide with some further direction. So thank you. Thank you for your time. Thank you again for the invitation, and I'll be happy to take questions.
Thanks. Yeah, you're bang on out of time, and feel free if people need to run, no guilt. But if anyone wants to stick around, any questions? Yeah, Luis.
I mean, this is super interesting. And yeah, I have many questions, but I'll just try to ask a few of them. Is there a p-norm distance between the integrograms?
Yes. Yeah. I mean, this is work that Justin Curry and I have been doing with 2 students at Albany, Robert
Okay.
Cardona and Tung Lam, and so we've the work is very influenced, of course, by the stuff that we've been finishing up with Havard in tandem, and yeah, there's a clean story that these guys essentially have worked out already.
And you would have like a stability like the one you have. I'm thinking of the 1 parameter case with the p-norm of the functions.
Yep, you have stability there, and it's pretty trivial, actually. Scribe and Turner, I don't know if I mentioned this, but they have to do a bit of work to get their result, and whereas in this case, I believe you don't.
Right, right. What happens if your functions are defined over a real plane, or like not a CW complex? Because you have this norm for functions defined as CW complex that is very kind of discrete. You just sum over each cell. What if your function is defined over the real line or something like that, where you already have a measure?
Right. So I'm not sure if I have much interesting to say, except I'll mention that this earlier Wasserstein stability result for for functions, for Lipschitz functions that I mentioned due to Cohensteiner and company, that result is in that spirit.
Okay.
And they use the Lipschitz property to sort of control the craziness of what's happening there.
Right. Right. And do you know of any filtrations that are not stable with respect to the interleaving distance that turn out to be stable with respect to some p-norm interleaving distance, like multi-filtrations that, well, I guess degree rips doesn't have that property, but maybe some other.
Right. So let's see. So I believe it's easy to get mixed up about these kinds of things, but I'm pretty sure that our distance is an upper bound for the interleaving distance, because essentially because the LP distance on a vector is a decreasing function of P. So that would say that you can't hope to have.
Right. That my question doesn't make sense.
Yeah.
Well, it makes sense. And the answer is no.
Yeah, it makes sense probably backwards. You could imagine persistent module, or there's one point that's far away and you have a whole family of them, and the noise in the bottom is just all over the place and crazy. And Bottleneck will only see that one thing where they would look identical in Bottleneck distance, but they're chaotic otherwise.
Right. I see. Right.
Mm-hmm. Sorry to chime in with the pseudo answer.
No, that makes sense.
Does anyone else want to ask a question before I let Louis just berate the speaker? All right. Awesome.
Can I ask a question?
Sure.
Yeah, so first of all, thanks, Mike. It was really interesting. I was wondering, so I was planning to ask you if you could say more about what you expect to happen for the multicover bifiltration. And then at the end of your talk, you said you'd want to talk about this on a different day. So I don't know if you want to address this at all today.
I'm quite happy to talk about it today. It's just I ran out of time. So let me, since you asked about it, I feel justified in giving a brief summary of the story to that. And I'm going to share my screen once more. So
I'll use my powers to chime in and say, I'm gonna happily let you use the half-an-hour break in between talks until 4 o'clock to present this. But in the interim, I'd like to thank you again for an awesome talk.
Oh, sure. Yeah. Thank you.
It's fantastic. And I'm actually really looking forward to hearing the next 10 minutes as well, the addendum, personally. But thank you very, very, very much.
Sure.
So
maybe it makes sense to ask, well, okay, I'm gonna try not to let this be 10 minutes, but I'll go ahead and
you've got 15.
Right. So, okay. So I realize not everybody may know the multicover bifiltration. Alex does. So in answer to your question. So first of all, let me cite the work that allows you to actually make the pictures that I'm about to show you here. So these pictures come from a paper by René Corbet, Kerber, myself, and Georg Osang, just from this year. And it's a theoretical work, but it tells you that using some algorithmic ideas of Osang and Edelsbrunner from recently, you can compute this multicover bifiltration. And so I mentioned you have this this kind of clean stability result for the multicover bifiltration. It's a one Lipschitz stability result. But if you look at these data sets here, these are 6 data sets. Like, never mind the ones on the bottom. I meant to take them out of the slides, but I ran out of time. I think these are more relevant. So yeah, you have these point cloud annuli here, right? This one this one has 100 points, or this one has 95 points, this has 190. And then we take those and just add a few outliers. This has got 5 outliers. This has got 10 outliers. And drawn here, plotted here, are the Hilbert functions of each of these guys using using first persistent homology. And there was some light coarsening done to the module so that we could stick them into this software rivet that allows you to visualize these. And to keep things simple, let's look at 190 points here and then with the 10 outliers. Here's what the Hilbert function looks like. The grayscale shading represents the homology dimension. And so all of this is dimension 1. So you see this big swath of gray stuff corresponding to this cycle here. And you can't tell from the Hilbert function, but all of this is persistent. And now look what happens when I add 10 points in. Now, to your eye, that doesn't change the structure of this very much. But look, all this like crazy stuff comes in. You get these big black stripes. So that's the kind of thing we want to explain. And so as a step in this direction, we have a pair of results, which first says that in brief, this result says that zeroth persistent homology of the multicover bifiltration is discontinuous for any p as long as you look at points in Rm for m large enough. So in particular, if you take p equals to 1, then you can take m, your embedding dimension to be 2. So you have this discontinuity result. So this, like in this realm, this is like really unstable.
Sorry,
in
can I?
that sense.
Can I interrupt? So pi is the Prokhorov distance, or what?
Yeah, sorry. Pi is the Prokhorov distance. Correct. I forgot to say. And these results are true either for the p matching distance or the p-Wasserstein. I mean, the p matching distance or the p presentation distance. And here we're using the Prokhorov distance.
Yeah, and so you can't call it d sub p because that would be too confusing.
Exactly.
Okay.
Exactly. Yeah, there's so many distances floating around in this stuff. And okay, but on the other hand, I think this result, if you think carefully, isn't so surprising, although the proof takes a good amount of finagling. If you restrict to, if this is a lot of words, but what it says is that if you restrict attention to point clouds of bounded cardinality, like what makes this discontinuity happen is that you like have these Prokhorov neighborhoods where more and more points come in with like small measure and they do weird things. And if you restrict attention to point clouds of bounded cardinality, this badness goes away and you at least get some kind of Lipschitz continuity here. But the Lipschitz constants are big. They're not 1 by any means. They're big. And so that kind of explains like the badness of these pictures, if you want to regard that as badness. So I think hiding in both of these statements are more quantitative bounds that would maybe explain to you like why you can expect to get this amount of nastiness with just the point clouds of these size, but I haven't written that down. And then, by the way, this also holds for, these results both hold for the Wasserstein distance on point clouds, if you prefer that. But again, like this was gonna be, we spent all this time like writing this, thinking it was gonna be in this paper that's coming out. And then the paper started getting long. So we decided that it's gonna go in another paper later. But so yeah, this will appear in the world eventually. Okay.
Yeah, thanks a lot. That's interesting.
Maybe I unshared my screen too quickly, but so you can't see anybody when you have your screen shared.
Right.
Yeah. Yeah. Thank you for the good questions.
Maybe I'll ask a question.
Please.
So I saw that you mentioned an LP homotop interleaving distance.
Yep.
what do you want it to do? Like, is there actually refine some specific stability result?
Yeah. What do I want it to do? I mean, it should reduce to the interleaving to the homotopy interleaving distance in the p equals infinity case. Should be an upper bound for like if you apply homology, that should be an upper bound for our p-Wasserstein distance. Maybe I want some kind of universality. Yeah, I mean, it should play a similar role that that homotopy interleavings play in TDA, right? Like, I don't need to tell you this, but philosophically, like when you do TDA, most of the things that you would like to do on modules, you could, at least in the theory, you could also do on the level of diagrams of spaces, and like that's a point that I've really like taken some pain to try to articulate in some other work of mine, and now here's this work that says nothing about that. So in the future, you would like to make everything go on the level of spaces, and yeah.
So I think the reason why I asked is that you have this, you said in one of your results, like in this generalization to 2 dimensions of the Scraba-Turner result, you cannot do all the eyes at the same time.
Right.
So one thing you may hope for the p homotopy interleaving distance in the 2 persistent case is that it is bounded above by the LP norm between the functions on the CW complexes.
Yeah, I feel that without having thought about it very carefully, I think that the prospects for this being true are good. I would guess that you have something like this. Yeah. Of course, you have to figure out what the definition is. There's like a certain amount of thinking to do there. And by the way, I'll mention that's something that we're starting to look at Albany as well, with this with the same group of collaborators that have been looking at the dendrograms.
Right. Maybe I'll just say that it seems to me that there may be something hard about not being able to do something for all eyes at the same time with homology, but this homotopy interleaving distance would be doing everything at the same time, like all dimensions at the same time.
Yeah.
But
yeah, I mean, what's happening somehow, if you perturb a cell, that can like somehow change the algebra of the homology in 1 dimension below and in 1 dimension above, or in a dimension and in a neighboring dimension, put it better. And I think somehow, like it seems like if one was formulating things in a homotopy theoretic way, like you wouldn't be in a setting where that could happen. Like you won't even have these neighboring dimensions to worry about like you do with homology. Well, I don't know. I mean, like we haven't looked at it. Yeah, like it hasn't been looked into carefully yet, I would say.
I think we have to clear the decks for the next talk. Thanks very much, Mike. It was a great talk.
Thank you so much. Yeah, thanks again for having me. And yeah, thank you everybody for listening and for the good questions.